For the next application of network flow, we're going to consider the maximum independent set problem. And in the maximum independent set problem, you are given an undirected graph, and your goal is to choose a maximum size subset of nodes such that no two nodes that you choose are connected by an edge. So for this example graph, we can see that if I mark the nodes I chose in blue, none of them are connected directly by an edge. And this is the maximally sized set of nodes that you could choose such that that property holds true. If we are trying to solve the maximum independent set problem, on a general graph, this problem is NP complete, and it's reducible from maximum click, because the maximum independent set will be the maximum click of the complement graph. However, in a bipartite graph, we can develop a polynomial time solution using flow. And this problem benefits greatly from using our perspective of minimum cut. So if we take the example before, and I label all of the nodes with numbers 1 through 9, and also two-color the graph so that we can split our nodes into two groups, the red and blue groups, what we can do is we can make the bipartite matching graph that we're used to, right? So we will connect, for any red node, we will connect it to the blue nodes that it shares an edge with in our graph. And we will add those edges in our flow graph with infinite capacity. Then for any red node, we will connect it from the source to that node with a capacity of 1. And for any blue node, we will connect it to the sink with a capacity of 1. It turns out that if we make this flow graph, that the cardinality of our maximum independent set, the size of our maximum independent set, ends up being the size of our original graph, not including the source and sink nodes, minus the maximum matching, or minus the flow of this bipartite matching graph that we've constructed. Now, why is this true? Consider any path from source to sink. What that path represents is two conflicting nodes that are both in our set. If we have not cut the edges that connect them to the source or to the sink, then they are in the set. And so in order to remove a conflict, and in order to remove all conflicts, our only option is to cut the corresponding edges that connect the source to a given node. And by cutting that edge, it represents removing that element from the set. In order to fully disconnect the source to the sink, we need to cut some of these edges or remove elements from our set. And since the flow will give us the minimum cut or the minimum weight edges that we need to cut, it turns out that the flow of this graph will give us the minimum number of elements that we need to remove from our set to get a set that does not break our independence property. And so the maximum independent set will be the number of nodes in our graph minus the matching of this graph, which is given by this flow network. If we change the middle edge capacities to 1, it doesn't actually change the answer, since each left node only receives 1 unit of flow that it can further propagate. But setting these edges to infinity allows for a better conceptual understanding, as we can't actually remove those conflicts. However, if we were to generalize the maximum independent set into something called the partition problem, we can actually see that each of the 3 different types of edges in our graph, which we can label X, Y, and Z, where X are the edges that go from the source to our red nodes, Y are any edges that go between a red node and a blue node, and Z is any edge going from a blue node to the sink. The weights of these edges actually represent different penalties that could be occurred from a chosen set. And so you can generalize your maximum independent set problem by applying different penalties for each of these different edges. For example, if we were to say that you could allow for certain conflicts with a given cost, instead of the middle edges being infinity, they might be whatever cost you are willing to accrue for that conflict occurring, or that pair of nodes both being in your set at the same time. And so the maximum independent set problem turns out to be a restricted version of this generalized problem where the penalty for not including a node is 1, and the penalty for including a conflict is infinity, because we're basically saying we cannot include any conflict, and if we are trying to minimize the minimum cut, we are trying to minimize penalties, the size of our maximum independent set will be whatever is remaining and whatever we don't remove.